Thanks for coming.
Okay, welcome to the September Astronomy Club of Akron membership meeting. Today we have our annual telescope seminar, and we have three great speakers that are going to talk to you about binoculars, refractors, and reflectors. During the break, please take an opportunity to take a look at some of the telescopes and binoculars that we brought in. Dean's got some really nice binoculars he has set up here that he's going to be talking about. We have, it's at least 1955, somewhere between 1950 and 1955, Celestar 4 by Fecker. So this is a real classic old telescope. We have a Unitron 114, it's a 62 millimeter refractor. And take a look at this eyepiece selection that we have here. So this is what they were building. This is also like 1950 to 55, somewhere in that range. Earlier model, a C5 Celestron, the single arm Celestron that John will be talking about for catadioptric. And let's see. So we're going to start out with Dean Phillips. He's going to talk about binoculars. Dean is a relatively recent member, but very helpful out at our star parties, talking to the public about all types of celestial objects and helping them out. So he's been very helpful at our star parties. Then we're going to move to Phil Creed, you've probably seen Phil before. Not only does he know a lot about astronomy, but he's a comedian. We love his jokes, but he's helped us out tremendously, done a lot of presentations, and we just can't say enough about Phil. He's a great guy. John Crilly, longtime member, and he has really secured the 16-inch. He was behind that 16-inch telescope getting it in our observatory. He worked out deals with Meade and had a special going over of that assembly, because John, he was a consultant for Meade, and we know about Meade. They've had some issues with first being bought out by Orion. Now everything's kind of in limbo, but John was doing a lot of consulting for Meade. They would send telescopes out to John. He would check them out, write reviews, and they would change telescopes based on the design, based on what his recommendations were. But also done a lot. He was president of the club, vice president of the club years and years ago, but very helpful for our group and out at the observatory. So let's start out with Dean Phillips talking about binoculars. And
thanks. So, binoculars they're a great place to start for new people that are interested in astronomy. Many of us already own a pair at home, or you notice my small collection up here. I used to work at First Energy. We'd have occasions when we're out there doing things like line patrols and things like that, or engineering, and binoculars helped a lot. I amassed a small fortune in binoculars when I worked for them. So there are a lot of advantages to binoculars, especially for new folks. Images are upright. Up is up, down's down, left's left, and right's right. You're not trying to flop some of those adjustments. You get to use two eyes. We're all used to using two eyes. Many of us in here have 40, 50, 60 years of practicing with two eyes, and only a few hours of practicing with one eye. And so one of the ways to really kind of illustrate that is this binocular, and these binoculars are essentially the same thing. They're both from Vortex. They're the same thing, and if you try both of them, you'll find out those are a whole lot easier to see through than the binocular is. So it's a neat idea at work. There was less stuff we were carrying around, but stuff just didn't look as good. It's a magnified view, so you get a little bit more magnified view than with your naked eyes, but also it's a brighter image. So the bigger that objective lens is, the more light you're going to collect, and so the brighter that image is going to be. And other applications, whether it's someone like me, I used to work for a utility and use binoculars, sporting events or hunting, fishing, whatever, outdoor stuff, or just as my niece puts it, spying on your neighbors. Spying on your neighbors, yeah. So, so there's some disadvantages. Weight. That big pair there it's heavy, and it's you basically have to use it on a tripod. So holding them steady, especially as they get heavier. Awkward viewing angles. It's easy to look at stuff that's flat out there, maybe up 15 degrees or something like that. But trying to look at stuff directly overhead, you can lay on the driveway and look at stuff directly overhead, but it's really hard to look at that stuff that's about 45 degrees up. Nothing quite fits well. There is limited magnification. These are 25 power. So you have to put them on a stand, otherwise you can't hold it steady. You have to put it on a tripod. My tripod is broke, that's why it's short and not up higher. The legs don't lock in anymore. So you kind of have to use it, sitting in the driveway or something like that. Getting them adjusted. It's for those of us who have played with binoculars before, there's a dioptic adjustment on one eyepiece. And so you look through it with one eye closed and you focus it, and then you close the other eye, and then you adjust the dioptic on there. That sounds easy and stuff like that, but imagine trying to, do this with a bunch of 8, 9, 10-year-olds that don't quite get that stuff. And then getting them adjusted as far as, the distance between pupils is, there are a couple things there that add to the complexity of getting them adjusted for people if you're doing something like a star party. We've done a couple small ones. The Ohio Veterans Memorial is in my backyard. We've done a couple small events there for some of the other members or some of the other volunteers, kids and stuff who come out. And then it's hard or impossible to do much astrophotography with them yet. Yes, you can get the clamp that goes on to the eyepiece and line your iPhone up and everything else, but it's far from a perfect or good solution. So kind of when we talk about brighter, when we talk about that with that naked eye, you can in a dark sky sight with naked eye you can see 9,000 stars, but you really can't see 9,000 stars because half of them are on the other side of the Earth. But so you can see about a third of those at any one point in time. But if you get a pair of 50 millimeter binoculars, that jumps up to 121,000 stars. So a lot more stars you can see, especially if you're not in a truly dark sky sight and stuff. 80 millimeter binoculars, you got 34,000 stars. I think these are 100 millimeters, so we look more than that. But it kind of gives you an idea. That's one of the advantages. I was out the other night, and with the pair of binoculars, I couldn't figure out what I did with because I had a little pair like this. These are 10 power, which is too much. I had a little pair like this, or 6 power, out the other night, and it just brought in just enough light that you really see the Milky Way. It wasn't that magnified or anything else, but just brought in just enough light you can see the Milky Way very well. And so as you start to look at binoculars, you have things like the power. It's a little bit different how a telescope's measured. So typically they're like a 10 power, 8 power, 6 power, 12 power. The objective lens, so you see that like 10 by 42, so the objective lenses are 42 millimeters. Exit pupil size, some binoculars just have really small exit pupils, and they're hard to get lined up with your pupil. And so things like the interpupillary distance between your eyes becomes more critical to get that adjusted right. Field of view. So it's fun. These things have a 3-degree field of view. And so if you're looking at something like Saturn or Jupiter, it moves about 15 degrees an hour. And so if you have that 3-degree field of view and you start out right in the middle, it only takes about 2 minutes for it to start to fall off the side of the field of view. So you have to keep readjusting for that. Yeah, you can put this on a star tracker or something like that, mount it onto that tripod. You're adding a lot more complexity to what hopefully would be a simple solution to get out and just do some stargazing. So eye relief, these all have a little cup under that turns to give you a little more eye relief or less eye relief. Typically, for most people, it would be turned out so you have a lot of eye relief there. And then if you're trying to use glasses, turn them so that they're in, so your eyes are closer. And then, the proto prism and roof prisms, it basically look like this. There are prisms in these designs that look like they're straight through. They're actually prisms inside there. And then on what we all think is the more traditional binocular like these, you can see where the prisms are in there. That's what helps bend the light around so up is up and left is left and right is right. The exit pupil distance. Usually binoculars don't tell you under what the exit pupil size is, but it's one of the things, and it's lining it up. Yeah.
Could you define the term exit pupil?
Yeah. So basically, when you look through binoculars, you'll see there's a circle that the image is a circle, and it's how close that circle lines up with the circle of your pupil. And so if the exit pupil is too big, you have light landing on your iris that doesn't get into your eye. If the exit pupil is too small, you have light that only lights up part of your retina, and so you don't get a full image. So there's plus and minuses.
So they have to be somewhat equal in size?
Yeah, you're shooting for something fairly equal. Every now and then you'll look at binoculars, and especially cheap ones, you'll look at it and say, oh, it has an exit pupil of 3 millimeters. That's a little small. Yeah. But if you're using them during the day when you're out in the light, it's not that bad because your pupil's already dilated. But for astronomy, that's a little small. So what can you see with binoculars? Double stars, bright asteroids. You can do some planetary viewing, daytime planetary viewing. The moon. The moon was really fantastic last night. I was out farting around looking at the moon. Star clusters and some nebulae. Satellite passes. Not last night, night before the International Sky. The space station went over the night before. Comets, we do have a comet that may be making its appearance here in a couple months. Stuff, and then, as my niece puts it, the neighbors. And then there's just some references in there. That's it. Any questions?
How much do the big ones cost?
I borrowed those from a friend. Maybe $250, something like that. Probably less than that.
What would you recommend for a novice looking at the sky in binoculars?
I'd say, if you already own binoculars, what you have is what you start out with.
What do you recommend for your neighbors?
Yeah. So I got my brother a pair of these for his birthday one year, and that's what started my niece talking about looking at the neighbors. And looking at your neighbors with binoculars is probably a little more stealthy than whipping out your telescope.
I have a weird question. I wish I would have brought these with me. I got a pair of binoculars that appear to be straight through. And I was told they were quite good ones, that they were a gift at work, some award or something. But I always had trouble with getting a single image in them. Is that something about the way they're made, or I just haven't found it there?
Yeah, so one of the things for terrestrial viewing, going out here looking at birds or something like that, the image is bright enough and there's enough information in the image. Your eye is probably going to do a fairly good job of lining two images up if the tubes aren't collimated with each other. But when you start looking at stars, I borrowed another set of these from my friend before before I borrowed those from him, and it was double image. I couldn't use them. Everything I seen, there was 2 stars up there. There were 2 moons. There was, but for terrestrial viewing, it was just fine. My eyes would line stuff back up. So it's one of the known problems with celestron binoculars. If you drop them, they'll fall out of collimation, and you have to send them back. Because his were fairly new ones, and he says, can you call up Celestron and see about sending them back? I said, yeah.
These are minerals.
Yeah, they wanted $75 plus shipping both ways on his binoculars that were still under warranty. Yeah.
Do you have any comments on image stabilized binoculars?
No, I've used them. Yeah, I did have to give those back when I left First Energy.
Did they work well?
Oh yeah.
Dave
Yeah.
Jesse used to have a pair, and then I bought them from him, and I like them. I wanted a higher magnification though, because where it really shines, I think, is at the higher magnification, where it's hard to hold regular binoculars steady enough. So, like beyond 10 power, like 12 or higher, I'd say they're pretty great.
How does that
Below
work? Is
that-
it electronic or what?
It's just like the in mirror stabilization for a
Yeah,
camera.
the prisms are,
Yeah.
gyro stabilized.
Yeah, we used First Energy. We use them. The big place we have people use them is in helicopters and stuff. But they're like 6 power. They're not very high powered at
Yeah,
all.
hardly needed for
Yeah.
6 power, but yeah.
But yeah, that's when I've tried them.
And they're expensive, aren't they?
They're expensive, and the ones we used, they plugged in. You were tethered to a power outlet.
Would there be an advantage of stereoscopic over mono, like some objects being 3D?
Well, so it'll kind of give you almost a 3D-ish concept there. Like I said, so I've got a binocular, and there's one up here like that, and then the ones on the tripod are binoculars. They're almost exactly the same thing, from the same company and everything else. The research says it's about 1.4 times better to look with both eyes than one eye. So I can tell you it's better. I can't tell you how much better it is. We'd had someone who had the wild idea of buying a bunch of the binoculars for us that worked because they were considerably cheaper, and no one liked them.
Where does one buy binoculars?
Anywhere.
Dick's Sporting Goods,
Yeah.
Dick's.
Yeah. Dick's Sporting Goods. Is it Time and Space? Is that the place down in? Yeah, down in
Mail order is, I mean, if you want it like Celestron,
Yeah.
then you probably have to go mail order.
Yeah. Yeah, or like we were just, Time and Space is a place down in Amish country that has an interesting, eclectic,
Time and Optics.
or Time and Optics. Interesting, eclectic store to go into.
You can get a budget pair there, or you can get a really
Yeah.
high-end pair there too.
Yeah, I had swung by there when I was getting ready to do some Eclipse talks. I stopped. I was going to buy some Eclipse glasses. They just like, here, have 40 of them. so, thanks.
Thanks.
Oh, so one thing I will point out. So most of these style binoculars that are center hinged, you can actually take the medallion off the front, and you can get a tripod mount like this. It's on this one. It's a quarter screw tripod mount, so you can mount them on a tripod.
I do appreciate the fact that those tripod mounts are dirt cheap too.
They are. They're like $12.
But even on a 50 millimeter pair of binoculars, they do help
Yeah.
a lot of times.
Okay, so next we have Phil. And while he's setting up, I just want to mention one other thing. Over on this table, after we're done, when we take our break, also has some interesting old binoculars. These are really old. These don't have any adjustment, like Dean was talking about. When you look through binoculars, it's not supposed to look like you're when you're looking through binoculars, it's not supposed to look like a movie where you see two
Like I say, it
fields of view.
knows.
You're supposed to adjust them so you bring those down, they match both eyes, and you have one field of view with both eyes. You're not supposed to see two. So this particular one does not have that adjustment. But as Dean was saying with the ones he was showing you, here's another pair. These are also very old. Take a look at these. You see how that's adjusted? So you adjust this to your eye so you bring those two field of views into one single one. And also over here, I brought some old, well not old, these are, well this is like a 1960s eyepiece if you want to see this. And this is something you've probably never seen. These were made by Celestra and they're probably about 25 years old. 60 millimeter eyepiece. I mean, it's unheard of. You can't buy these anymore. Not commercially at least. And this is an 80 millimeter eyepiece. So that's like really crazy, but Phil will tell us about why this isn't the best choice because of the getting.
Do you want me to seg right into eyepieces or just?
No, go into binoculars. I just wanted to say that these are on display at the break if you want to take a look at them.
Well, the bad news is I'm incredibly nervous when it comes to public speaking. The good news is that's actually not true. After you've done a while of these things, you just kind of get used to it after like the first, 5 seconds. So I'd like to welcome you all to our annual telescope seminar, and now I'm going to talk about refractors. And when it comes to telescopes, if I just simply mention the word telescope to the average person on the street, this is what their mental image of the telescope is, and that is a refractor. And layout for a refractor, pretty simple. You've got a lens up in the front. We call this an objective. It gathers light, it bends light, brings it all to a focus, and then we put our eyepiece there. So, just like this happens to be oriented this way, this is where the objective is. In this case, it's a 62 millimeter lens, gathering light. Down here is where we have our eyepiece. Pieces, plural, that's quite a few of them. And that is, it's the basic, very basic design. Big lens in front, little lens in the back. Couple of pros and cons of refractors. Like again, their image quality is great. They punch above their own weight in terms of aperture. The more aperture you have, the more light you gather, the more you're going to see. But all things being equal, a 4-inch refractor is going to show you more than a 4-inch reflector or a 4-inch telescope of any other design. Namely because you do not have any other mirrors in the path. It's an unobstructed design. Aesthetics, it just, it just looks like a telescope in your mind. And not only that, these look kind of nice when you have them out in your living room. Okay, you put a refined scientific instrument on a nice, especially one of these things, an old wooden tripod. It just, there's an extra oomph there. One thing that's nice about these things, since you're going to be looking at something that's up in the sky, you're going to be down here. And in a lot of cases, especially when this thing's pointed up rather high and the eyepiece is down here, you're in a seated position. You're very comfortable. For wide field observation, particularly when you're dealing with a short tube refractor, refractors generally have shorter focal lengths than other telescopes designed. So that means you have less magnification for any given eyepiece. So that does mean you have the trade-off of having less magnification is a wider field of view. So when you're scanning up and down the Milky Way, particularly looking at star clusters or large nebulae, refractors, particularly short tube refractors, they're great for that. There's no fiddling with refractor. There's no collimation. A lot of other telescopes are compound designs that require 2 or more mirrors to be aligned, you don't have to worry about collimation with a refractor. If you do find yourself where you do have to worry about collimation with a refractor, then life is going to be rather interesting. Yes?
On the collimation, I had 120. It has an eyepiece thing you put in there and inside it. There's 3 screws on front. You have to get your lens square it up center. So what they mean by I think they know collimation means for the smaller scopes.
I would say that in general you don't need to collimate a refractor.
I think the bigger
It's,
scope means
yes, in some cases you do, but generally speaking you don't. Like with the Newtonian, I would usually collimate the thing like once every time I go out, or once every other time. go
I
out
would
with a
point out
refractor
the
or not.
refractor needs to be in collimation. It's just you never have to do it because they stay in collimation.
Mhm.
When it leaves the factory, it's right, and it should stay right.
And that's the other reason why that I put that last point up. They're preferred for astrophotography. I've done serious astrophotography for the last 6 years, and I can tell you, even if I just simply ignore the telescope design in question, astrophotography itself is hard, and you don't want to be adding complexity to the equation on top of it. So having a very basic design helps. So those are the pluses. What are the minuses? Well, the minus one is pretty obvious. The thing about a refractor is that lens has to be perfectly figured. It has to be supported it has to be very carefully supported on the edge, and the glass has to be top quality throughout. So the result of this, and there's a couple other reasons I'm going to get into, but this is the most expensive design per inch of aperture. Once you get beyond 6 inches of aperture, refractors become prohibitively expensive. I'll give you an example. If you want 8 inches of aperture, an 8-inch Newtonian is going to set you back about as much as a set of new brakes. An 8-inch refractor is probably going to set you back about as much as a new car. Okay, but in the range of common refractors, which is typically in the range of 60 millimeters up to about, and nowadays up to about 5 inches, maybe a little bit more. In that general range, they're more expensive, than a Newtonian of that aperture range, but they're becoming a little bit more affordable. But it doesn't change the fact they're still the most expensive design per inch of aperture. The other thing now, remember how Dean was talking about the fact that when you use a pair of binoculars, you get a nice right side up image. It's intuitive, okay? With a refractor, because you're using a diagonal to take the optical path into your eye, what that means is that you're going to get an image that is right side up, but mirror reversed. So, the first telescopes that we ever pointed toward the sky were refractors. This is a Galilean telescope, and he actually made several of these things. One of them had aperture that was all the way up to a whopping 1.5 inches. That's it. And pretty low power instruments. I think his went up to something like 25 or 30 power. That was not a huge, not a powerful instrument by any means. But to say that it literally opened up the universe to humanity, it just totally rewrote what we knew about the heavens. And it was the same design, just big lens in front, eyepiece toward the back, little lens towards the back. Unfortunately, there's this pesky thing called the laws of physics. A refractor is called that because it refracts, it bends light. Unfortunately, light waves do not bend the same universally. Your shorter wavelengths, like your blues and your violets, are going to bend to a different extent than your long ones, like your reds. So the result is that they don't focus on the same spot. So if you were looking at a bright object, you would see like a kaleidoscope of color around them if you're just taking just one lens and trying to make a telescope out of it. We call this chromatic aberration, or false color. If you see online discussions about refractors and they list CA, that's what they're talking about. we're talking about false color. So the thing is now how do you solve that? Well, the thing is that if the ratio of your focal length divided by your aperture, which is what you call your F ratio, your focal ratio, if that's really, really, really long, then you can tame the false color. But there's another problem. That focal ratio, that also grows with aperture. So the result is that if you want twice the aperture, you're talking 4 times the, you're talking 4 times the focal ratio. So the result is that these scopes really, really start getting long. The picture that you see right there is a refractor by Johannes Hevelius, a Polish astronomer from the 17th century. And I believe this is the one that he made where it had a 120 millimeter aperture, which is 4.7 inches. It was 140 feet long. Whoa. So, these things really, like I said, it's just amazing that we did any kind of astronomical observations back then at all. Things started to change about 200 years ago. What became popular was what's known as a Fraunhofer doublet. And this is a case where your outer lens was a crown element, and then you have an inner lens that's flint. Well, the result of this is that it helps bring the colors a lot closer together. Achromat, by the way, means without color. And it wasn't a perfect design, and it's still a case where your focal lengths really have to start getting longer and longer and longer with increasing aperture. It's just that these focal lengths were a lot more manageable. Now the picture I have right here, this is the refractor at Lowell Observatory in Flagstaff, Arizona. That's a 24-inch achromatic refractor. Again, not perfect. You're still going to get some false color around a lot of bright stars, but it's a lot better than it was. Now, a special kind of achromat is these wide field refractors, and these are typically short F ratio refractors. What I have pictured right there is an Orion 120 ST. It's at F5, which for a 4.7 inch achromat is nowhere near long enough focal ratio to really get you to tame the false color. You look at something that's bright, particularly like a star like Vega or Sirius, you're going to see more purple than a Prince concert. However, false color really shows itself on bright stars and at high powers. For low powers, it's nowhere near the issue. In a lot of cases, most times, if you're sweeping with a wide acro at low power, it's pointless. You're not looking for false color. It doesn't become an issue. They are uniquely suited for sweeping star fields at low power, particularly under dark skies. The funnest night I ever had with any one individual telescope was an Orion 120 ST from Cherry Springs. Just beautifully dark sky. I had a cheap achromatic refractor. Now I'm surrounded by people that have got like really high-end refractors, people that have like, you know, astrophysics refractors, Takahashis, and I'm there just, you know, with that little thing. I feel like somebody who's driving a rusted out pickup truck through the Hamptons. But after a while of being embarrassed about it, I just started to embrace it. I'm like, hey, you know what? I know this thing's a one-trick pony, but that one trick, low power, wide field sweeping under dark skies, it does that one trick really, really well. So, again, if you love looking at a lot of big objects, a lot of star clusters, and you like going to dark skies, these things are great. You know, again, seated position, and a 4.7 inch refractor, which that is going to show you more than a 4.7 inch Newtonian will. But the thing is that eventually we got around to really purging the color. Phil Harrington, the astronomy author, once joked that achromatic translates to no color, apochromatic translates to no color, we really mean it this time. these became dominant in the 21st century. Up until about, I'd say probably the 1990s, your typical refractor was an achromatic refractor. Most people just simply couldn't afford a design that was color-free. This right here, this Unitron, this is a classic achromatic refractor. It has 62 millimeters of aperture. Its focal length is 900 millimeters. Okay, so running the math in my head, that's about an f14. Okay, that's a pretty long f ratio. These tubes were not long because somebody in the marketing department said they need to be long. These tubes are long because it had to be long enough to tame the false color for a 62 millimeter lens. But then we came to extra low dispersion glass, or ED glass. And what this does is, if you take an ED doublet versus your standard achromatic doublet, you're going to have anywhere between 1/3 to 1/6 the amount of false color. So now this was a case where you could have a color-free design in a system that was much, much, much more portable. Now again, it's one of those cases, it still scales up exponentially in weight and in money and length when it comes to increasing aperture. But again, you're talking about something that's a much more manageable design. You can see the difference right here. Some people's eyes are not as sensitive to false color as others are. But one thing that is very unforgiving are 3.76 micron pixels that you're going to find in common digital sensors these days. They're as unforgiving as the balcony hecklers from the Muppets. And you might, oh, well, there's a little bit of false color that I can see to my eyes. Your camera's going to see a lot, okay? But I don't want you to, I mean, you're not going to look at this and just be aghast if you see it visually. You'll see a little bit of false color, but it's not like, you know, in most cases, it's not just, you know, screaming at you. But with an apochromatic refractor, no false color. You're seeing a true color image. And these things are very popular. Imaging has largely taken over the astronomy market in general, and particularly when it comes to refractors. So you now have telescopes that will give you a color-free image. They're very compact. They use, a lot of them use high-end ED glass, so like FPL 53 or FCD 100. And a couple examples of this are up here. This is an Astrotex AT60ED, 60 millimeter aperture, 360 millimeter focal length, so it's f6. And this thing right here, if you retract it, because the dew shield will extend out, if you collapse the dew shield, you're talking about something that, with minus an eyepiece or a camera or diagonal, is only about 9.5 inches long. When I brought this thing home, my wife said, "Oh, it's a baby scope." And from that point on, I've called it baby scope. But it does pack a punch. And particularly when it comes to imaging, it packs a punch. Now, if you want something that's, okay, for visual, like I want a little bit more aperture, but it would be nice if I could hook up a camera to it. One of the better ones out there is this one. This is an Astrotech AT115 EDT. I think they might, I don't know, does anyone know if they're still running a sale on these things? But
I'm not sure. They don't make mine anymore. Mine's the 111. They hold their value pretty well.
Yes, these, this thing right here, I know when they were running a sale, you could get this for $11.99 shipped, brand spanking new. And if you look on the used sections of Clyde Knights or Astor Mart, these will routinely pop up for about $900 used. And considering the fact that you're getting an apochromatic 4.5 inch refractor, that's something that was science fiction 25 years ago. And like I said, there's a couple other examples. They're still not cheap. I would hesitate to call a refractor that costs $1,200 to $1,400 an impulse buy. But relatively speaking, in terms of what you're getting and historically how much a color-free refractor of that aperture would have cost, it's nice, it's refreshing to know that that's still within, that's something that's within the reach of mere mortals like myself. Does anyone have any questions on refractors? Yes?
Could you say a little bit more about this ED glass? Because in the field of optical glass, I think there's really a breakthrough that I've seen over the years.
ED glass has only been used in refractors for only, I think, for about the past 40 years or so. And what it meant, what I mean by dispersion is that, okay, if we know that these wavelengths are going to bend differently if they're red versus purple. Well, if they disperse, if the difference between how they bend is a lot less, okay, that's why it's referred to as extra low dispersion glass. Where these things started to become popular was, I mean, I think the first ones that regularly did this was Takahashi. And they had, technically they weren't using extra low dispersion glass, okay, because I'm sure somebody who's got a Takahashi will correct me on that one. What they were using was fluorite. Okay, fluorite is not a glass, it's a crystal, but it has very, very, very low dispersion. So it's real easy to make a telescope using just two lenses, one of them made out of fluorite, that has low enough dispersion to give you a color-free image in a reasonably compact package. It's going to cost you a lot, but you could. And then some companies, notably Astrophysics out in Illinois, started to make ED triplets. And then they're still very, very expensive. Where the breakthrough came is when China decided to start making triplets and doublets with ED glass. And that's when the costs really, really started to come down. And there's different grades of ED glass. If you want to talk about grades of ED glass on cloudy nights, especially in the refractor form, you're almost better off talking about safer things like politics and religion. I'm only half joking. You would not believe some of the rather heated discussions that will come as a result of, like, well, I just think, I don't know about FCD 100 versus FPL 50. And you'll just see, like, oh, I see that it's now 15 pages now on this thread. Okay. Generally speaking, if you're talking about FCD 100 or FPL 53, if your telescope has that in there, you're going to have really good color correction. Period. Yes?
Got two questions. So I've been looking at some of these April telescopes. And I've seen FPL 51, and then also, you know, doublets are obviously cheaper than triplets.
Right.
So can you comment
Okay.
on those two things?
Okay, a doublet and triplet is just basically what the name says. Doublet means you got two lenses, two elements in the objective lens. Triplet means you got three. All things being equal, you're going to get better color correction out of a triplet that has the same F ratio versus a doublet. And again, all things, in other words, if I have an F7 doublet versus an F7 triplet of the same aperture, let's say it's a 4-inch telescope, the 4-inch F7 triplet is going to have better color correction than the 4-inch F7 doublet in general. The catch, though, is that if the doublet is made out of the higher end stuff like FPL 53, then you're talking similar color correction to a triplet that's made with the lower end glass like FPL 51. Generally speaking, an FPL 51 triplet and an FCD 100 or FPL 53 doublet, same F ratio, they're going to have comparable color correction. Because I know some people ask, like, this is where this question comes up. What, do you want an Astrotech 102 EDL or an Astrotech 115 EDT? Because the latter is F7 triplet with the lower end FPL 50, FK61. The Astrotech doublet, the AT102 EDL, that is a doublet using the higher end FCD 100 glass. If you're just doing visual, if it's an ED doublet, generally speaking, you're good enough. It doesn't even really matter what the glass type is. If you're going to use it for both visual and imaging, if it's a doublet, you want to insist on the higher end glass, the FPL 53 or the FCD 100. If you're doing a triplet, you can get away with FPL 51 or FK 61. Good question, though.
So you would say stay away from an FPL 51 if you're going to do any kind of dash.
If it's an FPL 51 doublet, I wouldn't. I go ahead and use it for visual, but I wouldn't necessarily. You're not going to get the best results if you're doing astrophotography. I won't go as far as to say you can't use it for astrophotography.
I get it.
You could use it. You can use an Orion 120 ST for astrophotography if you want. I wouldn't recommend it.
Clean up the.
Right. I mean, you can punt the ball on 2nd and 5. I wouldn't do it, but I'm just saying you can.
Sometimes that's the best play.
Sometimes it is. Yeah.
So I'm assuming that it's the primary lens that is the expense. You were saying as they get larger, they get extremely expensive quickly.
Right.
And
Very
that's probably
quickly.
because of the doublet and triplet lens.
Well, if you're talking about, let's just simply say, the easiest way to look at it is, if you go back to this kind of design right here, an achromatic doublet, okay? To keep those things color-free, they generally wanted an F ratio that was 5 times their aperture in inches, okay? So let's say, for instance, you had a 62 millimeter lens. That's a 2.5 inches of aperture. Okay, so if I want to keep that design color-free, if I want to get below a certain, actually that standard is called the Conradi standard. If I want to get the false color below that point, 2.5 inch aperture means I want a 12.5 F ratio. So my aperture times 12.5 has to give me my focal length. Well, here's what, okay, so you're talking in a situation like that, you would get a focal length that would come out pretty close to that, to about 900 millimeters. That's not too bad. Let's take, however, a 5-inch refractor. If it's a 5-inch achromatic doublet, crown and flint, if I have to have a suitable F ratio, now I have to go to F25. My focal length has to be 25 times the 5-inch aperture. So now I'm 125 inches. So now I'm talking about a refractor that's 10 feet long. So you can see how these things, so not only, and it's not just that, no such thing as a free puppy. Even if I handed you a telescope like that free of charge, now you have to mount the thing. Okay, and now you have to find a suitable mount. You probably need an observatory at this point. You're not going to be chucking that into, you know, a Chevy Trax. And
All of this is because the reason you want the bigger, wider lens is to get more light.
right,
And then you want to make sure all that light is also color-free.
right. And that's the thing. Is like that's the reason why these things have just. That's why whatever you can do to shorten that focal length. That's why that's the reason why your extra low dispersion lenses. That's why they're very popular. I mean to get the same kind of color correction of that 115 EDT. That's an f7 refractor. So it comes out to about this long. It's very portable. A lot of medium-sized mounts will handle it just fine. But if I want the same color correction out of a standard crown and flint doublet, okay, now I'm talking like about an f20. So picture something that's about 8 to 9 feet long. Yeah.
How important is this cringing problem considering you can correct everything in Photoshop?
Good question. His question was, how important is the color error or the dispersion, since everybody nowadays is like, you know, using Photoshop, PixInsight, and whatever high-tech sorcery to manipulate the images in the end. And the answer is, it's still very important because you still have to start with the foundation of having good quality data. And if you've got a lot of false color in your images, you know, there's only so much you can do to correct that. Again, astrophotography, as hard as is, you know, it's better just to simply start off with something that doesn't need to be corrected for color error right out the gate. There is a little bit of wiggle room, yes, but if you, like I said, if you try to shoot with like a wide field acro, okay, there's going to be a lot of false color in your images. There's just no way around that, unless you're shooting with a mono setup, and that's a whole different can of worms. Okay.
Thank you.
It has what we call a spiderless secondary mount. You have to have a mirror in the center that reflects the light out toward the eyepiece. And normally that is held by a spider. 3 or 4 veins will come in from the sides and the mirror is mounted to them. And we'll talk about why that's less than ideal. This uses a spiderless. The focuser assembly actually has a secondary mirror holder on it. So when you install the focuser, the secondary mirror shows up in the right place and there's no structure. So the light has to get past this mess, which is less than ideal, but you don't get the same kind of effects you get from spider veins. These are some of the reflectors that I've had around my place over the years. Here's a typical portable setup. It's on an equatorial mount, a German EQ mount, modest size, probably about a 6-inch. Dobsonian mounts are very popular for newts and very, very, very economical, unless you let it get out of hand and let it get too big. That's a 20-inch newt that I used to carry around with me to star parties. Or if you don't need too much aperture, but you want lots of focal length, you can make them that are really, really tall. Even though that's a 10-inch, that's a 12-inch. But they're relatively, we say fast. They have a shorter focal ratio. Or I'm sorry, they're relatively slow. They have a longer focal ratio. So I think that one was maybe F10, F12. I think that was F10. This was F3.8, so it's very short and stocky. It's very short for the aperture. And so Newton decided we can make a reflector wherein, you see I mentioned the struts that hold the secondary mirror suspended in space. Light comes in, hits the parabolic mirror, reflects back forward into the secondary mirror, which shoots it up the eyepiece, and that's where you see it. And here you can see the 3 spider veins. Disadvantages, as Phil pointed out, there's junk in the way. In a refractor, the light comes in, goes through the objective, goes into the eyepiece, and you look at it. You don't lose light by having it blocked by something, but that's not the big problem. The big problem is whenever light passes an edge, you get diffraction. You get diffraction effects. Even refractors exhibit a diffraction effect, but it's one that we don't think of and we kind of ignore. If you look at an image, and you'll notice that the brighter stars appear larger than the dimmer stars, that's an artifact. That's not true. That's a diffraction effect from the light entering the aperture. When it comes in, it has to pass this edge. It has to pass this edge. And I'm blocking some of the view. Let me step back a little. And passing that edge is a diffraction effect. And it causes the star, instead of being a perfect pinpoint, it causes the star to acquire a circular appearance. We can never resolve the shape of a star. Stars are too far away. They're not nearly big enough to have a resolvable shape to them. Stars are pinpoints, astronomically speaking. You could never hope to resolve a star as anything but a pinpoint. Anytime a star looks like bigger than a pinpoint, that's diffraction effect. That's not real. The telescope did that. And it's it's actually wrong, but you have to live with it. Every telescope's gonna have an aperture, it's gonna have an edge. But with the Newtonian, we get that. So your brighter stars appear larger than your dimmer stars, which is false, but universal. But you also have light passing these spider veins. And you have light passing the edges of this mirror. You get diffraction effects from that. In the case of the spider veins, the diffraction effects are obvious. When you look at an image and the star's got spikes sticking out of it, typically 4, sometimes 6. Those are caused by diffraction hitting those veins. When the light gets diffracted by this vein, it's going to appear on the image as one long spike. This one's going to make one long spike that way, this one's going to make one long spike that way, which means you're going to have 6. These 6 diffraction spikes, that's for a three vein spider. When there's 4 veins, they coincide. So you don't get double the amount, you just get 4 spikes, but you get them twice, so they're more intense. And that's just life with a reflector. The secondary has to be mounted somehow. As I say, in this case, you won't get the spikes from the diffraction from the veins, but you still get some asymmetrical diffraction from the fact that there's a mount between the focuser and the mirror that extends into the path. That's just life with newts. You can get around it, talk about that later, but that's it. New reflectors have their characteristics. The magical thing about Newtonian reflectors is, well, color control was obviously an important thing, and the fact that they scale up. You can make an 8-inch Newtonian reflector very cheaply today, and it will work well, and you can have a fast focal ratio. It can be f4, so it can be physically short, 32 inches long. You've got an 8-inch scope that actually works. Refractors, they don't scale up worth a darn. Lowell proved that. We saw a picture of it a little bit ago. We saw Lowell's 24-inch refractor. 24-inch achromat would have to be about half a mile long to work well. His was not. His was extremely fast in terms of how fast it would have needed to be to have reasonable color control. On that particular telescope, if you look through filters, red, green, and blue, the focus point between red and blue on the focuser itself is a couple inches different. They're dispersed that greatly, you can't have all 3 colors anywhere near in focus at the same time. It means you don't get the kind of chromatic aberration that we normally see, which is this purple haze, because on that one, it's so very much too fast that it's beyond a purple haze, it's just gone. That light's just scattered. So you don't notice chromatic aberration. Really, really there. 24-inch new, well, I had one, had a 20-inch, and it was only that big. A tiny fraction of the size of Lowell's machine, and yet what you see in it is real. It's real. This way, way, way too big and way, way, way too fast achromat caused Lowell considerable embarrassment various times. In order to control the chromatic aberration enough that he could actually see well at high magnification, he had to mask it down to a very, very small aperture. 3 inches, I think it was. In which case, you might as well have had a 3-inch refractor. He would mask it down to 3 inches to get a long focal ratio to control the color. Trouble with that is there's artifacts in your eyeball when you're dealing with an exit pupil as small as what that resulted with. Exit pupil, good thing to be aware of. When you're choosing your eyepieces, especially your binoculars, exit pupil is the aperture divided by the magnification. You can do that in your head instantly anytime you're wondering. So you can figure the On Lowell's refractor, as long as it was, and with a 3-inch aperture that it was masked down to, the exit pupil would have been just barely anything. The eyes get artifacts when the exit pupil is way too small. And that's why I published pictures of surface details on Venus that he certainly never saw. And that's why I published charts and graphs of canals on Mars that he certainly never saw. As soon as real astronomers got to looking to see, to try to verify his stuff, it wasn't there. So that's the hazard of trying to scale up a refractor. It doesn't work well. Biggest refractor I ever had was a 7-inch epichromatic. And it was really long, it was F9. So whatever 9 times 8 is, it was long. It was heavy. Views were sweet. I liked it. But gee whiz, it just exactly fit in my observatory when it was parked. It almost touched the east wall and it almost touched the west wall. It just barely squeezed in there. So I didn't have that forever, and it was heavy. But it was cool. I like big refractors. But as Phil mentioned, you get into the 8-inch, and yeah, you could be looking at a compact car. There are people that own them. Probably people own bigger ones. I know people with 8-inch epichromatics, and they paid for them. 8-inch newt. Hey, here we go. Right there. 8-inch newt on an Dobsonian mount. A lot of us, when we're recommending first telescopes to people, well, everybody should probably start with binoculars. We're in the sky a little bit, but when you're ready for a telescope, a lot of us say, get yourself an 8-inch Dob, 8-inch Dobsonian. When I was recommending them, they were what, $250? I bet they're no more than $350 today. 8-inch telescope, you can see a lot with an 8-inch telescope. I think I have a slide that talks about that. Although today, a lot of people say instead, which it lines up with what Phil was saying, a lot of people are saying start with an 80 millimeter refractor. You're not going to get the great planetary views, but you get those pretty wide field views, and you'll see a lot. And they're lighter and cheaper. Well, I don't know they're much cheaper than an 8-inch Dob by the time you put a mount under it. But it's another way to go, certainly more affordable. But I like an 8-inch Dob for a beginner. My first telescope was an 8-inch Dob because somebody told me to do that, and I did. And I'm happy with that. Phil mentioned a Star Party experience. I was at Great Lakes Stargaze at a dark site up in northern Michigan with an 80 millimeter APO refractor I had just bought. And I spent the entire night gazing through that thing. There's a lot to be said about a short 80 millimeter telescope under clear dark skies. But we're talking newts here. I got shifted. The next thing that happened after Newtonians was Cassegrainian reflectors. Cassegrainian reflectors happened because people wanted a long focal length because they wanted great magnification, especially if they wanted an image where you can't do much about. In imaging, the focal length tells you the magnification. That's all it is. You can't change eyepieces to change magnification. It just is what it is. So if you really want long focal lengths, they started making Cassegrainian reflectors. Cassegrainian reflector starts off working like a newt. Light comes in, it goes past a stupid secondary, which blocks some light and which causes some diffraction effects. But you gotta have it. It's your parabolic primary mirror. Comes out here to a secondary mirror. That can be anywhere between a spherical section or a hyperboloid section, which is anything beyond a parabola is a hyperboloid. And it shoots out through a hole in the primary mirror to where the eyepiece or camera is behind here. The advantage is you can get a lot of a lot of focal length and a very compact design. If you look at this thing, this is not a Cassegrainian reflector exactly, but you can see what happens. We've got the secondary mirror here, which is in the wrong place because it's a Schmidt. It should be it's in the wrong place because it's a Schmidt. Never mind. Anyway, the light comes through. It goes through a corrector plate that would not be there on a true Newtonian. It's a spherical primary mirror, which would not be there in a Newtonian. It should be hyperboloid. It's another spherical mirror here and gets it zodded out the back. Just like that. In the classical Cassegrain, both mirrors are paraboloid. If you took them both and pushed them all the way past paraboloid to hyperboloid, it would be a Ritchie-Chrétien. If you relaxed them to where they're less than parabolic but more than spherical, it would be a
Schmidt?
Dahl-Kirkham, I guess.
Oh.
But the problem was, until the last decade or two, parabolic mirrors, and especially hyperboloid mirrors, were expensive and difficult to make. And spherical mirrors were easy to make. So then somebody says, well, let's go to a combination telescope. Let's switch over, let's use spherical mirrors, and they use glass to correct it. And that's why you wind up with a combination. It has both reflective and refractive elements in it. And they look like this. That's probably that's a 14-inch that I used to have in the observatory. It's a 7-inch that I used to have in the observatory. It's a 10-inch that is sitting in my living room for unknown reasons. How they work is, light comes in, it goes through this corrector plate, which is a very, very, very mild lens. It's just corrects for spherical aberration. Light hits this spherical primary, comes up and hits the secondary and out the back. The advantage is we got away with a cheaper spherical mirror. The disadvantage is that this lens is a fourth order curve. It's very complex. It's very thin, it's very light. Material cost is very very small. But making them adds a lot of your cost back. The good news is, even though that's the lens technically, you can see it's very thin. It doesn't do very much. It does not cause chromatic aberration. It's you can ignore it in terms of that. So we can call it in effect a reflector. The other thing about these is their primary is very, very fast. F2 maybe. And then the secondary is curved to have like a 5 times multiplier, so you wind up with F10 out the back. And that's how this is configured. You've got this corrector plate out here, and a 5x spherical secondary, and a 2x spherical primary. This particular Celestron C5, the 5-inch Schmidt, Celestron kind of won the amateur market very, very quickly when they came out with the Next Star 5. They used this optical tube on a very simple one-arm mount with a go-to computer in it. And they sold pretty cheap, and they were very light, they were very portable, and they sold like hot cakes. Suddenly the C5 was something to be really contented with. They eventually increased it up to a C8, an 8-inch on a similar mount. But the Next Star 5 made Celestron. That took them from just another company to a real successful company. In fact, one that's still around. Back in the 60s, Celestron and Meade were battling it out for the Schmidt market. And Meade's gone today. Celestron's still around. I guess they won that battle. Another way of doing it, if you wanted to have a spherical primary, I'm not very good at pointing this thing. Maxitoff in the 50s Maxitoff decided that you could use a spherical corrector too. It has to be pretty thick, and they are. They're thick and heavy, and they're very sharply curved. This is spherical curve. Light goes through. It gets manipulated a little bit going through it this way, and then it really gets manipulated bouncing off of this surface. Sometimes there's actually a reflective surface here. So light goes through the corrector to the mirror and then back out through the corrector again. Different versions of the Maxitoff design. The Maxitoff has a disadvantage of it's a heavier, thicker corrector. It has the advantage of it's spherical. And we know it was possible to make spherical surfaces inexpensively long before it was possible to make the more complex surfaces. And optically, it's much simpler than the Schmidt corrector, which, as I say, is a fourth order curve. But they're heavier. And in order to work well, they have to be slower. Typical Schmidt Cassegrain is going to be F10. Some enhanced Schmidts out today are F8. But a Schmidt or a Maxitoff Cassegrain is always going to be F13, F15. Just has to be slower to work well. Same with the classical Cassegrain, actually.
These also, you lose the diffraction spikes with those.
Yeah, the fact that the reflection is happening on something mounted to a lens, you don't get diffraction from anything mounting the secondary. The secondary just is. It's in the right place. Valid point. This design, there we go. Classical Cassegrain, these had to be real slow. Classical Cassegrain in the 8 to 10 inch range is always going to be F12, F13, maybe F15. And that's why Ritchie and Chrétien decided they wanted to be able to make it faster and thus shorter focal length. So you push both mirrors to hyperboloids, and now you can be F8. So that's why the Ritchie Chrétien have.
What's the advantage of being F8 versus F13?
If you're imaging, where there's not going to be an eyepiece involved, the question is, what are the advantages of being F8 instead of F13? One advantage is you're going to have a greater field of view if you wanted a greater field of view, because it's going to be shorter with the F8 thing. The other thing is, and these were designed for picture taking or imaging, the difference in exposure time between F8 and F13 is vast. And every f-stop, you pretty much double your exposure time. You're going from 8 to 13 is a bunch. Imaging at F10, I've done it. I didn't like it. Imaging at F11, Celestron's 14-inch Schmidt is F11. I've done it. I didn't like it. Imaging at F8, yeah, that's my comfort zone. I can take the time to image at F8. I'm using an astrophysics mount. I mean, I could shoot as long as I want to. I don't have to worry about mount errors. But then again, I only get so many hours of darkness. I'm in Ohio.
Question.
Yeah.
Yeah, but I'm completely new to this, so I'm your target audience.
Perfect.
You talk about these F numbers, and then you also talk about faster and slower. Are these two concepts related?
Yeah. When we talk about a low F ratio, F4, F5, F2, we call that fast.
Okay.
And we talk about F13, F15, we call that slow. And we call it that because of the exposure time.
For imaging.
Yeah, at F13, it's slow.
Okay, so it's all about imaging.
If we start talking fast and slow, and those terms actually we picked up from the terrestrial photography guys. They talk about fast lenses and slow lenses. So we just kind of pick that up when we're talking about imaging. It is not nearly as important when you're talking about a telescope for visual use, where you can change the eyepiece to get the effect of a longer or shorter focal length. But there's limits. the maximum achievable field of view is determined by the focal length. If you really, really want wide field, and your telescope's f13, you're only going to be able to go so wide, half a degree, maybe a degree. Whereas if it's really fast, which means a really short focal length, 5 degrees is easy. I've shot 5-degree fields of view using a fast refractor, Takahashi. But I've never had a combo telescope faster than f8. But f8's good. It's a nice round number. You're going to have a focal at reasonable apertures in an f ratio of f8. Your focal length is going to be in the 1500 to 2000 millimeter length range, and that's a nice focal length for imaging. If you've got that and then another telescope that's 600 millimeters, you're home free. And that's what's on my mount at home right now. I've got a 10-inch f8 modified Schmidt, and I've got an 11-inch f2 Roe Ackerman, which is about 600 millimeter focal length. And that gives me two different fields of view that I've always been pretty comfortable. If I get somewhere around 2000 and somewhere around 600, I can shoot whatever I want to shoot. That's just a nice range for me. Let me skip past the mounts because we'll talk about them another time. Here's what happens with aperture. And these are stolen from Celestron with permission. Just to show you the kind of resolution that you get with increased aperture. 3-inch scope, looking at the moon, that's pessimistic. You can see the moon better than that in a 3.5-inch scope. But they blurred it on purpose to approximate what happens. With a 14-inch scope, the resolution is so much better. Aperture buys you two things. It buys you increased light gathering, meaning you can see dimmer, but it also buys you resolution, as in net. Again, looking at resolution, typical blob, 2.4-inch telescope. As we step up in range until we get a lot of resolution at 8 inches is a nice round number. It's middle ground. You see a lot in an 8-inch telescope, but the 14 shows more. Magnification. How much magnification do you need? This is for optical use. At 50x, it'll be the size of a pencil eraser, maybe. 100x, 200x, 400x. 400x is magical thinking. At least here in Ohio, maybe in the Keys, where things tend to be more stable. Around here, on a decent night, we call it seeing. It's a measure of how unstable the upper atmosphere is. We're normally limited to 150, 200x. You try to blow it up bigger than that, it's just empty magnification, because you've already got all the resolution that the sky will permit. But on a magical 400x night, and we have them in Ohio, you just can't count on them, but they exist. You can blow it up that big. That's what increased magnification can buy you.
What magnification do we usually see if we're visual on observatory stuff?
Ron?
The 40 millimeter, which is what we've been using, that gives 100x. And then if we use the 31 millimeter Nagler, that gives 130.
So, any questions? Let's see, I dazzled them. Go ahead.
Yeah, so I have a Newtonian Dob, and I find I need a collimator a lot. So I've read around a little bit, and there are some solutions out there. And supposedly some of these Dobs are designed so you don't have to collimate very often. Do you have any? I mean, usually it's getting thicker spiders that are more rigid. But do you have any recommendations and/or experience with how to?
Yeah, it depends on what you've got. I mentioned earlier that refractors. He's asking what can you do to make a Newtonian retain collimation better? Refractors retain collimation extremely well. When you buy it, it's in collimation. and 10 years later it still is. That's why we say you don't collimate refractors. Not that they don't need to be in collimation, but you never have to adjust it. On a newt, the primary source of collimation error on a newt is either the primary mirror mounting. It needs to be rigid. It needs to be really, really rigid, and yet it needs to be adjustable. So they generally will have 3 collimation screws that push a corner of the primary out, and there'll be springs to try to hold it there, and you're pushing against the springs. A sloppy mirror cell that doesn't hold the thing very reliably can really change your life. Or sometimes on the larger newts, the size of the secondary gets a little bit big and they get a little bit heavy. And the structure of the spider vanes that support the secondary can be weak. In some cases, if the focuser is really, really, really cheap, it can move around. Any one of those 3 in your collimation shot, I would suggest put the laser on it, or get somebody to look through a Cheshire or something to gauge how the collimation is, and then wiggle things. If wiggling the primary does it, you want to rebuild that primary cell. If wiggling the focuser does it, you might want to spend a couple $100 on a really premium focuser, which you can keep and use on your later telescopes if you upgrade. And if the spider's doing it, you might want to make sure it's really, really tight. But there'll be something that you can tap on or wiggle and you'll see it, and you'll know that's where it's coming from. And it can all be improved. And thanks for starting with a dot, because I really, really believe in that. Anything else? Cool.
Thank you.
Great job.
Thank you.
Yes. Okay. All right, are we ready to go?
Yes.
Okay. Well, just when I thought I was out, they pulled me back in. Going to talk real briefly on eyepieces. The thing about observing or imaging through a telescope is sometimes we make the mistake of referring to a telescope as kind of a singular entity. And perhaps the better way to think of this is more along the lines of a system, okay? And having good components throughout the system is going to help. For instance, if you had a gaming computer, for instance, you would have, it's nice to have a top-end gaming computer that's really, really fast, but having a crappy monitor attached to it is not the best thing. So you want to have good components all throughout. People like to say, hey, the eyepiece is half the telescope in a sense. The eyepiece is just simply what allows for visual observation. And this is a very personal thing. When I give advice on these things, I try to make it, I try to lay down some more basic concepts, but this is a very personal thing, and depending upon what you're looking at is largely going to determine the kind of eyepieces you're going to want. Good way to characterize eyepieces in terms of importance, barrel size. It would be really awesome if the eyepiece that you spent perhaps a decent amount of money on actually fits in the focuser. So it helps to know what your barrel size is. The focal length of the eyepiece is critical. I'm sorry, I apologize in advance, we're going to have to do a little bit of math. I promise you it's not going to be that bad. The eye relief, it helps if you can actually see the entire field of view when you put your eye up to it. The apparent field of view is also important, makes the difference between whether or not you're looking at the standard eyepiece view, a really wide view, or a soda straw. And if the eyepiece itself has nice tight stars throughout most of the field of view. Okay, barrel size. Most of your telescope focusers have either 1 1/4 or 2 inch sleeves. So that's where your eyepiece sizes are going to be nowadays. If you were looking at telescopes that were 50 years or older, some of them are going to have 0.965, but nowadays they sell them in 1.25 and 2-inch eyepieces primarily. This right here, this barrel that you see, which is this section right here, and oops, and this is on this eyepiece right there, that is an 1.25 barrel right here. This just uses just an 1.25 barrel. So if I have an 1.25 focuser, I'll put this in there. A lot of focusers that are 2-inch focusers will also have 1.25 adapters, so you'll also be able to put in there just fine. That eyepiece, incidentally, I actually have that in my case. That's a pretty good eyepiece right there. That's 17.5 Morpheus. That has a dual barrel. That has a 2-inch section right here. So if you just had a 2-inch focuser and you didn't want to put an adapter in it, you could just slide that portion in and it will hit that ledge right there and come to a stop. So this is something, the common question I asked was like, oh, well, what power is that eyepiece? And the thing is, technically, eyepieces don't have power. It's going to depend on the eyepiece, it's going to depend on the telescope you're putting it in. Your magnification, the power is just simply the focal length of your telescope divided by the focal length of your eyepiece. So to give you an example, let's say I had a 1,000 millimeter focal length and I had a 20 millimeter eyepiece. I would have 50 power, just like that. The telescope that I have at home has it's an 8-inch f5 Newtonian, has a 1,000 millimeter focal length. So for this particular eyepiece right here, which is a 5.5 millimeter Meade, that's 182 power. Now for this particular telescope, that Unitron, which had a 900 millimeter focal length, if I put the same eyepiece in there, I'm now down in the range of about 160 power. And generally speaking, you want to avoid powers that are more than 50 power per inch. So like on that 8-inch, so on my 8-inch telescope, I don't want to go beyond 400 power. There's a variety of reasons. One of them being, in most cases, the atmosphere is just simply not going to support 400 power. If you live in the Florida Keys, God bless it. You could probably use that power on a lot of nights. Around here, you can't. The other thing is that 50 power per inch, your background sky is going to be looking really, really, really dim. And when you get to really, really high powers, problems within your eye, notably floaters, they really become a lot more apparent. Focal length selection, and I'm just putting this up there just for just a general guide. This is for most telescopes, namely refractors and reflectors. Doesn't quite necessarily count for the Smith Cassegrains, but for most refractors and reflectors, low power, you're looking at 20 millimeters and up in terms of focal length. Now again, it's focal length divided by the focal length of the scope divided by the focal length of the eyepiece. So if the denominator, which is your eyepiece focal length, is bigger, your magnification is less. So low power eyepiece, you want to be looking 20 millimeters or more. Your 2-inch eyepieces give you your widest view. So if you have a telescope that has a 2-inch focuser, this is where it will really come in handy. Medium power, 10 to 20 millimeters, and high power, generally single digits. Okay, and this is just kind of a broad recommendations here. But these are only general guidelines. You also have to factor in something that we've already mentioned, which is the exit pupil. So I want to show you what this thing actually does look like. Okay, if you just simply take an eyepiece and you just kind of lay it on its side, you're going to get a nice big circle of light. Pop it in a telescope though, you get a tiny little circle of light. The diameter of that circle is what your exit pupil is. Now when Dean was talking about binoculars, and just take your aperture divided by your magnification. If you have a pair of 10 by 50 binoculars, 50 millimeter lens, 10 magnification, 50 divided by 10 is 5 millimeter exit pupil. Pretty straightforward. Now remember, what we got to do here is, okay, so magnification is telescope focal length divided by eyepiece focal length, and now I have to look at the aperture of the telescope. There's a quicker way to do this. Most telescopes will tell you what the F ratio is, and that's really all you need to know. Your eyepiece focal length divided by the F ratio, there's your exit pupil. So if I have an 8-inch f6, which is a common Dobsonian, and I put a 24 millimeter eyepiece in there, 24 divided by 6, 4 millimeter exit pupil, done. As far as your exit pupil, you go larger than 7 millimeters, you're probably looking at wasted aperture. Chances are, actually, if you're my age or older, getting above 5.5 to 6 millimeters is, I think you had that chart in there.
Yeah.
You or John had the chart in there, an exit pupil. You don't want your exit pupil to get too big, because you're effectively wasting aperture. You spent the money to gather all that light, but if your exit pupil's too big, it's not going to go into your pupil. If your exit pupil gets much below 1 millimeters, then you get a really, really dark background. If you're thinking, well, I'd like to get some eyepieces, but man, I don't even know where to start. I'm not sure where I really want to prioritize the funds. If you're going to prioritize an eyepiece selection, get one with an exit pupil between 2 to 3 millimeters, or 8 to 12x per inch of aperture. So I'll give you a good example. That 8-inch f6 Dobsonian, if you're looking at 2 to 3 millimeters of exit pupil, that means you want to have somewhere between a 12 to 18 millimeter eyepiece. That focal length right there is going to be the one you're going to prioritize. That's going to give you your best overall blend of utility in terms of like a good image scale, a decent amount of magnification, but your sky background isn't too dark.
Bill?
Yes.
Can I ask one question on the exit pupil? So, yeah,
You just did.
if you go too big, then you're wasting light. But for people that are unstable, especially beginning astronomers, is it better to have a little bit wasted light and then they can find it? Where if you matching it right up against your the pupil of your eye, then if you drift a little bit, you get a black spot.
I've heard, they're different, I have different, I kind of vacillate on this thing admittedly. He's asking, like, you know, if you're starting off, you're kind of novice, does it help to just put up with a little bit of wasted light and then, you know, just to have just that really wide field of view and just kind of move your eyeball around a little bit? Well, you're still going to have wasted light no matter what. However, if you're just trying to find the target, a lot of people have like a really, really, really low power eyepiece for no other reason, just basically to say, okay, do I have the object in the field of view? Okay, I can always bump up the power later, but do I at least have the object in the field of view? And there is something to be said for that. I mean, I'm admittedly a little bit, I kind of waffle on that thing because there's a part of me that also says that's where having a good finer scope helps. But the flip side is you might have a sky that's not dark enough for you to even see the object in the finer scope. Like, well, I think I've got the right star field, but do I not? I mean, do I know for sure?
I'm thinking like more like a person that maybe never has looked through a telescope. Maybe people that come up to the observatory, they never looked through a telescope, and they're looking and they say, I can't see anything because their eye isn't lined up directly.
Right. And
So
that will help.
If you have a little bit bigger.
Yeah, if you've got a bigger target, you don't have to be as, yeah, that's true. He's got a point. If you've got a bigger target, if you've got a bigger exit pupil, you don't have to be that precise in lining up your eye.
It kind of gives you that porthole
Right.
look.
And the same thing with binoculars. I mean, a tiny exit pupil means you have to get that interpupillary distance set much closer.
Everything's got to be just lined up.
Yeah.
Otherwise, if you're not lined up, then you're going to see black.
Yeah, so in my case, I've got a gauge I pulled up and I adjust them so I'm not walking around trying to do this.
Of course, one thing that does help is being able to actually see anything at all. And this is where eye relief comes in handy. Eye relief just simply says, okay, it's going to come to a focus. Like where that exit pupil is, when you get a photograph of that exit pupil is not on the lens. That exit pupil, if you think about it, is actually floating above where that lens is. How far above is it floating? Because that's where you got to put your eye to actually see it. And that distance is known as eye relief. So if you got a lot of eye relief, you got this. If you have, you know, more or less middling eye relief, you got this. If you're using a 4 millimeter ortho, you will have a transcendental experience. Your eyeball will become one with the eyepiece because you essentially have no eye relief with one of those. I've done it before. It's not very comfortable. If your idea of comfort is eating a box of Triscuits after a tonsillectomy, you know, try observing with a 4mm ortho. Now, if you're using eyeglasses, like me, you want long eye relief. In some cases, if you just have eyeglasses that correct for nearsightedness or farsightedness, no big deal. Just take them off and just look through the eyepiece. Here's the problem. Most people like me who wear glasses don't just have nearsightedness, we also have astigmatism. And you're not going to correct that at the focuser. You've got to have the glasses on, or at least contacts or something like this. So if you wear glasses, you need to have the extra eye relief to account for the thickness of the glasses. Generally speaking, you want something beyond 15mm. So when you go shopping for eyepieces and you need glasses, look to see what the eye relief is. And as far as eye relief is concerned, that is most critical, especially if you have astigmatism, that is most critical with low power eyepieces. If you're using a 7mm eyepiece and it says 10mm of eye relief, and you got some astigmatism, you might get away with that. Why? Because your exit pupil is small. When your exit pupil is big, you now have to have the majority of your pupil gathering up the light, and your astigmatism really starts to show up there.
What's the eye relief on the observatory?
On the what?
The one at our observatory.
Which eyepiece is it talking about?
40mm
The Meade super wides, they're actually, I just happen to know that they're a scale design. They generally have roughly 2/3 of the eye relief focal length in eye relief. So like a 24mm Meade has about 16mm of eye relief. Well, 40mm Meade is going to have about 26, 27. So it will be plenty. Like if you need eyeglasses, it will be plenty.
So does that mean you have to move back if you're looking through it? Like, how do you know if you're looking through it at the right distance? I'm really new to this.
Good question. Okay, so when you see the full field of view and you get everything in focus, then that means you know you're in the right spot. If you've got 27, let's say you've got like an eyepiece that has 27mm of eye relief, which is quite a bit. That's that much. Okay. Well, if you're not wearing any glasses, it's very easy to go much closer than 27mm. It will start to black out. And if you pull your head back too far, it'll start to black out again. But if you get it just right, you'll see and there's usually a little bit of wiggle room. You know, they try to design eyepieces in these cases that you don't have to exactly hold your head in one spot. But you'll know it. I mean, if that's the reason why you can, it's just like anything else. You can have too much of a good thing. If you buy a 55mm Plossel for like a Schmidt-Cassegrain, that thing has 38mm of eye relief. I mean, it's almost like looking through a rifle scope where you're like holding your eye back like that. Good question. Okay.
So, sorry.
Yep.
If you do have glasses and you choose not to wear them, and you just focus it out.
You can focus it out to correct for your nearsightedness. But if you're putting the glasses aside, the focuser will only correct for nearsightedness. It will not help you with astigmatism. So now, if you don't have astigmatism, that's not a problem. But like I have like over a cylinder of astigmatism on my left eye, which is usually my observing eye. And if I take my glasses off and try to focus it, I'll get the stars in focus, but they'll all look like little seagulls, even in the middle of the field of view.
As you get older, a lot of times your distance vision is okay, but it's short vision.
Right. Yeah.
So what about that?
As long as you don't have astigmatism, whether or not you're nearsightedness or farsighted, it doesn't matter. You can actually do it without glasses. Yeah. I generally prefer to observe with glasses, especially if I'm doing public outreach for one simple reason. I know that my vision is corrected. And somebody else's who doesn't need glasses, I know their vision is corrected right out of the gate. So if I have a focus for my eyes, it's going to be focused for theirs.
Right, if it's just me and I have just barely a little astigmatism, I always focus for myself without the glasses. But to start parties, I use the glasses, figuring, you know, not everybody is comfortable with focusing, so.
Now, something that also is something that you hear about a lot more these days is what's known as apparent field of view. When you look through the eyepiece, try to imagine like the edge of the field of view is one side's over here and the other side's over here. Well, that angle that's formed between here, and your eye, like try to imagine that as a circular slice. That angle right there is known as your apparent field of view. Standard eyepiece designs of yesteryear, particularly like orthos and plausials, like this would be like a 10 millimeter. I think this is a plausil. This has an apparent field of view of about 50 degrees, and which is not too bad. If you look through something like a monocentric or eyepiece, those things have like a 25-degree apparent field of view. They look like a soda straw. The rage these days are wide field eyepieces. This is a Meade 5.5 millimeter ultra wide. This is an 82-degree apparent field of view. So it's like looking out a portal of a spaceship. So the three images of the Pleiades that you see, they're to the same image scale, to the same magnification. The difference is that the 82-degree apparent field of view, you have a just wider real estate. So the good news is, the more apparent field of view, you get a lot more stars around it. It's going to cost you more. You need more complex eyepiece designs to do this. Plausial designs are, like a typical four element eyepiece. You have two doublets, instead of plausials. So it's relatively straightforward. These things, on the other hand, they're a lot more complex. And again, just like eye relief, you can have too much of a good thing. Once you get past about like 80-degree apparent field of view, means like your field of view looks like this. So you can get to a certain point where like, I can't see the entire field of view all at once. Yeah.
Just one last question about.
Certainly.
Do you wear transition glasses, or you are progressive, I guess I should call them, or do you wear just regular?
I have a name for them that's less diplomatic than progressive.
Yeah, so what do you?
Demonic, infernal, regressive.
Yeah, progressive, right. Yeah, so does that causes some distortion too?
It can. I have learned.
In addition to the astigmatism.
Right. I have learned, basically from the mid part on up, I have my corrected distance vision.
Yeah.
So I have learned basically to view just looking slightly upward.
Okay.
It's just one of those
I have a
things.
horrible time.
I hate them. I've called them things that I cannot repeat here. I don't want children within a 2-mile radius to all be ushered in the doors, in an impromptu fashion. I don't like them, but
But you wear them.
yeah, I wear them.
You adjust them.
As a former president would have said, I feel your pain. So.
Is field of view set by the telescope focal?
No, the apparent field of view is strictly the design of the eyepiece.
Right, so is that telling me I'm getting 82 degrees of whatever the telescope is?
No, it just simply means that if you're looking through the thing, your apparent vision is 82 degrees, okay? That doesn't affect your magnification. Now, I will say this. Let's say, for some circumstance, let's say you had an 82-degree apparent field of view and you had 82 power. You would get exactly 1 degree true field of view, okay? So you would be able to fit the full moon in about 2 times in that field of view. Now, as far as eyepiece aberrations go, there's a common saying: good, cheap, wide field, pick any two. This is cheap, and it's reasonably good, but it's not wide field. This is pretty good. It is wide field. It's not as cheap as this one. So again, there's a trade-off here. If you're going to have an aberration in eyepiece, it's usually off-axis astigmatism. And it shows, you can see it right here. You see it looks like little seagulls okay? That is just simply a function of the eyepiece design. To correct it, you need more elements in your, and when you get fast telescopes below f6, this really shows up in a lot of budget, low-cost, wide-field eyepieces. If you're, I like to say everything's great above f8, because once you get in the range of like an f10 Schmidt-Cassegrain, a lot of affordable eyepieces are going to be sharp across the field of view. But once you're getting into f5s, you know, f4 Dobsonians, a budget wide field eyepiece looks ugly toward the edge, really ugly. I took a what was known as a Chinese, it was a Chinese sourced 1 RPD. It was a 30 millimeter, 80 degree apparent field of view eyepiece. I think it cost somebody like maybe 50 bucks, and I just borrowed it just to see what it would do on an f4.5 Dob. The seagulls that you see right there started about halfway to the edge. What was at the edge was not seagulls. It was something, it was some H.P. Lovecraft Cthulhu-esque things that should not be. And it just looked really, really hideous. That is the reason why a lot of people that have big Dobsonians, that's why they put premium eyepieces in there, just because to get the edge of the field of view sharp. It's not a necessity though. You can just ignore the rest of the field of view and just concentrate on the center. And those things, those better eyepieces, you're not going to get the off-axis astigmatism, but it's going to cost you more. Again, no such thing as a free lunch. One of the last things I want to recommend here is a Barlow lens. And what this is going to do is it's going to take your eyepieces and it's going to effectively increase the power of your telescope, usually by about 2x. That's the most common one. These things potentially can save you a lot of money. A good Barlow lens only costs you about $50 these days. But let's say, for instance, that you happen to have a 12 millimeter and an 8 millimeter Teleview Delos. And you want, like, well, I want to get a little bit further down just in case I want to look at planets or something really high power. A Teleview Delos costs you $370 retail. To get 2 of those things costs you $740. Now, if I want to get 2 more focal lengths that give you higher power, I'm looking at another $740. Or I can get a 2x Barlow lens for $50 and have the equivalent of a 6 and a 4 millimeter eyepiece. Because again, it doubles the power. Okay, the other way to think of it is you're given the equivalent of 1/2 of the focal length on the eyepiece. So just to wrap this up, a few good eyepieces is going to beat a huge collection of mediocre ones. You don't need to spend a huge amount of money, but you want to concentrate on like the middle power eyepiece. Again, something that's going to give you that 2 to 3 millimeter exit pupil. Don't stock up on 2-inch low power eyepieces. You want to have one good 2-inch low power eyepiece for most telescopes, or just have one good low power eyepiece, but you don't necessarily need to stock up on those things because there's only so many objects that you really need that huge of a field of view. And you want to add a Barlow lens just to kind of expand the range of your eyepiece collection, or available range of magnifications, but at the same time keeping the costs down. Are there any questions? Because that is the end of my presentation. Yes?
At this time, I'd like to put in a plug for the Teleview dioptrics accessory. It allows you who wear eyeglasses and also have astigmatism by just buying one Teleview dioptric, you'll be able to see through a Teleview eyepiece without your glasses. That's if you need glasses to correct your vision, and you also have astigmatism. Now they come in different strengths. You have to buy every strength? No, just buy the strength dioptrics accessory, that would correct for your astigmatism. Just wanted to point that out. Thank you.
I have thought about those. The reason why I tried not, as much as I want to, the reason why I didn't go for that was because if it changes, then I need another dioptrist. And if somebody is observing who doesn't have astigmatism, I have to remove it now. If you're somebody who is observing by yourself, particularly if you just don't want to wear eyeglasses, they're great. A dioptrix is better even than having a set of eyeglasses. Because you're not worried about like a sweet spot or anything like that. You're just, the whole eyepiece is basically going to give you a sweet spot. So, and I think that's it.
Thank you.
Thank you.